Okay, I think we can start. So good afternoon. Welcome to the people online. We'll have two talks. And the first speaker will be Jeremias Aguilera-Damia from ULB. And he will tell us about non-Fermi liquid quantum critical points in two dimensions.
Okay, thank you. Well, let me start thanking the organizers for inviting me to participate in this beautiful workshop. So today I'd like to tell you about a particular model that has been worked out in this series of papers. And essentially this model displays the interplay between quantum criticality and non-Fermi liquid dynamics. Yeah, thank you. So before going to a particular model, I think it's worth to spend some time introducing these concepts, namely quantum criticality and non-Fermi liquid dynamics. So this will be very imprecise, and I think we'll have a problem. Well, sorry for that. But essentially, quantum critical points sits at the phase transitions that occur at zero temperature between different phases of matter. So they occur at, in particular locus in coupling space, in which the structure of the ground state change very drastically, usually associated to some symmetry breaking pattern. So let me mention at this point that depending on the details of the model at hand, many of these couplings can be actually tuned by varying certain external parameters such as pressure, magnetic field, or even the chemical composition of a compound of the sample, as is the case with doping. So the main outcome is that one can usually tune a model or a system to criticality. And finally, a pretty obvious comment, but which will play an important role later on. So let me emphasize that thermal fluctuations doesn't play any role here. So do not confuse, for instance, with the case of magnetic orders destroyed by thermal fluctuations upon heating up a magnet, for instance. So let me go through a prototypical example, which is very familiar to all of you, probably. So I will try to go very quickly. Let's consider the quantum missing model. So assume you given a rate of spin degrees of freedom, whose dynamics is governed by the Ising Hamiltonian. Here, the first term is the usual exchange coupling, and J has dimensions of energy. The second term, which depends on this dimensionless coupling G, essentially measures the relative strength of transverse magnetic field. So there are two obvious regimes in which the ground state is qualitatively different. So on one hand, we may consider the case of having very weak transverse magnetic field. So in this case, the exchange coupling dominates, and we will have the spins will be forced to align in either up or down direction. So as it is known, this is a symmetry breaking phase with a Z2 spontaneously broken symmetry. So we have a twofold degenerate ground state, and we also have a long range magnetic order. So this is what is called the quantum ferromagnet. So the opposite regime, when the external magnetic field is very high, then the second term Hamiltonian will dominate. And so the ground state is now unique and symmetric, and there's no magnetic order. So, and this is the quantum paramagnet. So it is fairly clear that we cannot map continuously these two ground states. So something special has to happen at some point in the middle, and there is where the critical point is. But now back to generalities. So in general, what is the effective theory that describes dynamics at a critical point? So at this point, I'll focus in particular on phase transitions, which are second order. So we have some additional piece of information. In particular, we know that there's a typical energy scale associated to quantum fluctuations over the ground state. And depending on the model at hand, it may have many realizations, but what we know for sure is that it has to vanish with some prescribed power law, depending on some universal exponents at the critical point. So on the other hand, there's a correlation length, which essentially modules the exponential decay of the correlations. And we know that critical point, it has to diverge with a given power, prescribed power law, signaling the transition from short range to long range correlations. So putting all together, in general, this sort of critical points, the effective theory describes the dynamics is a scale invariant theory of some gapless degrees of freedom. And in particular, is the dispersion that these gapless degrees of freedom satisfy is given by this universal dynamical critical exponent Z, which will play a prominent role along this talk. But so far we have discussed about the zero temperature dynamics, but actual experiments are done at finite temperature. They might be very low, but it's still different from zero. So it seems that at some point this hasn't any phenomenological impact. But fortunately, this is not the case due to the existence of something called the quantum critical region. So let me give a very rough definition of what it is. So let's suppose that we have a quantum critical point at zero temperature, here where the red dot is. And so we know that there's some typical energy scale, which we call delta, associated to quantum fluctuations in the vicinity of the critical point. And if we heat up the system, then we introduce a new energy scale, which is temperature, and essentially sets the typical energy of thermal fluctuations. So it makes sense to compare these two, and we will find that generically there's an extended region above a critical point in which delta is less than the temperature. And this physically means that quantum fluctuations are still energetically favored. And so they dominate the low energy processes in this region. So given that, one would expect that certain properties corresponding to the critical point, one would expect these properties to extend to scaling behavior across this region. So a very important role is played by the limits of this region, what we call crossovers. So in general, one has lateral crossovers, which will be by definition the places where the temperature scales like the sun. But there's also a vertical crossover because quantum critical region cannot extend to arbitrary high temperatures. And this will be given by some dynamically generated scale, which we will see more precisely in the model that we will work out. Okay, this about quantum critical. But now let's talk about fermions, because in this talk we are interested about metals, which are models of fermions of finite density. And moreover, we will be interested in metals with non-Fermi liquid dynamics. So since non-Fermi liquid is it's defined in opposition to Fermi liquid, let me start saying a few words about what's a Fermi liquid and what's Fermi liquid theory. So let me start just reminding you what happens with a gas of free fermions. So if you have a gas of free electrons, you know that the ground state by the Pauli exclusion principle is organized in terms of a very big volume comprising all the occupied states piled up on top of each other. up to some energy scale, which is the Fermi energy or the Fermi momentum. But this scale is usually huge. So the main outcome of this simple picture is that these states living deep inside this volume are effectively frozen. So it's really expensive to promote one guy from here to analogous state out of this volume. Also, the low energy processes are usually dominated by or described by states in a narrow region close to the boundary of this volume, which is what is called the Fermi surface. So this simple non-interacting picture, it's enough to make some predictions. For instance, you can check that using just this, you can check that, for example, the specific heat has to grow linearly with the temperature, or for example, that the magnetic susceptibility is constant at low temperatures. But so far so good. But this model is it's free. It's not interacting, so it's not realistic at all. So it came as a big surprise when people realized that this simple non-interacting picture was enough to describe many experimental observations made in metals. And this was like a long-standing puzzle, and it was solved by Landau in the 50s when he proposed the liquid theory, which essentially states that it's based on a particular idea which is called Adiabatic Continuity, which in roughly speaking, one could state it as the fact that usual metallic systems, interacting system of fermions, at low energies will flow to a weakly coupled fermionic, a theory of fermionic quasi-particles. So let me disentangle a bit more what this is. But essentially, the idea behind this adiabatic continuity, it's very similar to what we've seen in the free case. So essentially what happens is that no matter how strong the interactions may be, as long as they are not singular, and it will be important later on, let's assume that, they can be very strong though. There's still a massive suppression of phase space for a given low energy scattering process. And due to this massive suppression, the quantum corrections are tamed in the sense that they cannot, even if they may involve large renormalizations of some phenomenological parameters like the effective mass, these quantum corrections essentially cannot change the analytic structure of the fermionic green function. So let me be a bit more precise about this. So in the case of a free fermion, we have essentially this sort of green function. And what is called the spectral density, which is the imaginary part of this, is essentially a delta function localized at the pole. So the idea of Landau is that in the interacting system, what one will have is a softened version of a delta function, but it's still pretty much localized. So the excitations are pretty much like particles, and that's why the name is quasi-particles. And moreover, the width of this distribution in the spectral density is proportional to the energy square, and this width is essentially the decay rate. So what he found is that at low energies, quasi-particles are essentially fairly long-lived, and so they are weakly coupled. So this is the main idea. This is an old one. So in a more modern approach, the same conclusion can be reached by scaling arguments. Very quickly, what you can find is that due to the fact that the energy scales only with the orthogonal separation to the Fermi surface, and it doesn't depend in other direction, this fact defines a very peculiar process. And under this decimation, one can check that any possible self-interaction is rendered irrelevant. So a theory of weakly coupled quasi-particles is very natural at low energies, and that's the reason about that's the reason for these theories to be very successful in describing generic metals. Within these successful predictions, for instance, there's a prediction for the scaling of the resistivity, essentially saying that the resistivity has to go with T square. This is pretty much related to the decay rate with the square of the energy. Another powers may appear, but what is true is that within Fermi liquid theory, you cannot obtain lower powers. So for instance, you will never find a resistivity which goes with linear with T. This will become important now, later on. And let me finish this very imprecise review of Fermi liquid theory by saying that it is, there's a loophole about the naturality of a theory of weakly coupled fermions. And this loophole is essentially because there still exists a channel of interaction, which is called the VCS channel, which essentially couples two quasi-particles in antipodal points of the Fermi surface. And moreover, this coupling can become relevant at one loop, so driving the system to a period stability, to a superconducting state. But these instabilities were studied a lot, so superconductivity out of Fermi liquid, it's quite well understood, and also led to very interesting predictions and successful as well. Let me just mention one here, which is that if I have time to speak about superconductivity, it will play a role. So this prediction is essentially that the superconducting gap and the critical temperature are essentially proportional to each other. There's no scale separation between these two. And they are usually exponentially suppressed by the usual dimensional transmutation. So at this point, one could ask, well, let me just say that I have a talk about Fermi liquid theory. Well, non-Fermi liquid theory is exactly whatever deviates from this theory of weakly coupled quasi-particles. More precisely, a non-Fermi liquid metal will have fermions, but will have no well-defined quasi-particles. We will see how this arises explicitly. But before asking ourselves about how can we get a non-Fermi liquid metal, we should ask first if there's any need to look for a non-Fermi liquid. And the answer is actually affirmative. And again, it comes by the hand of a groundbreaking experimental finding, which is the detection of the strange metallic phases, usually in high TC superconductors. So in order to illustrate this very briefly, I just include a schematic picture of the typical phase diagram of cuprate, high TC. So I want you to focus on the wedge-like region, the purple one, which is that strange metal, and it's dubbed like that precisely because the measurements there deviate from the predictions of Fermi liquid theory. In particular, in some cases, you can find something called Planckian dissipation, which essentially implies that the resistivity will have to go roughly linearly with the temperature, which is something that was ruled out by Fermi liquid theory. Well, something else that I can tell you about this is that usually this wedge of the strange metallic phase cannot be accessed at arbitrary low temperatures because it's usually hidden behind the superconducting dome. And something very special happens with these compounds is that usually highest critical temperatures occur when the superconducting dome overlaps the strange metallic phase. So it's quite reasonable or plausible, and it has been proposed some years ago, that there might be a quantum critical point at the tip of at zero temperature, and the quantum critical region associated with this critical point, which has to be non-Fermi liquid-like, maybe a plausible explanation for the phenomenology observed in these strange metallic phases. So now that we are motivated to look for non-Fermi liquids, then we can try to find a particular one. So in general, what would we need to add to our model to get the non-Fermi liquid? Well, for sure, we will have to account for some singular interactions relevant enough in order to destroy the analytic structure of the quasi-particles. As a bonus, it would be nice if this same interaction or a different one could account for a singular contribution to the BCS pairing in order to enhance superconductivity as well. And it turns out that coupling a Fermi surface with gapless bosons, which are the natural degrees of close to a quantum phase transition, do both. So that's essentially the strategy we will follow after this quite long introduction. So our task will be, first, I will try to describe you the critical point, which is non-Fermi liquid dynamics at 0 temperature. Then we will heat up the model and characterize the quantum critical region. And we will see explicit this competition between quantum and thermal effects manifest in the presence of static modes, static bosonic modes. And if there's some time, I will try to comment about implications for superconductivity. So let's go. So the model at 0 temperature, it's essentially consists on a circular Fermi surface. We are in 2+1 dimensions. So here the Fermi surface is just a line. We will consider it as spherical for simplicity. So it's a rotational invariant model. And near the Fermi surface, we expand the moment excitation. And so we end up with the usual Fermi liquid kinetic term for fermions. So you here. The second ingredient is, of course, a soft boson. So we will couple the boson by the Shukawa term to the fermionic degrees of freedom. And at this point, one should ask if, of course, a relativistic dispersion is always an option. But one should ask if this is robust at low energies, and it turns out that it is generically not. To gain some intuition, for instance, one can check at usual fermionic loops at finite density induce terms which will dominate over the frequency squared term of the relativistic dispersion. This particular contribution, which goes with the frequency over the momentum, is called Landau damping. So the moral of this little exercise is that we will consider overdamped bosons just from the outset, spirit of effective field theory. So in order to do that consistently, we introduced a mass scale, which we call the Debye mass. And essentially, it acts as a unit cutoff for our effective theory in the sense that for energies below the Debye mass, which we will consider it's large enough, so for energies below the Debye mass, the bosons will have essentially this dispersion relation, which is accounted by Landau damping. Let me remind you, we will consider the model tuned to criticality, so there are no mass terms for the bosons. So we end up, in order to make some contact with the instruction, we could say that we end up with a Z=3 boson, essentially because the dispersion relation it's omega proportional to Q to the cube. And so this is, in other words, that the boson has Z. So our model is just a Fermi surface with a Z=3 boson. And let me just comment these bosonic modes with the non-relativistic are pretty common when they, in the case where there are some other parameters fluctuating near a quantum critical point, so this is something very crazy. Finally, we have a problem because the system as it is strongly coupled. Fukuoka interaction in dimensions, it's relevant. So we need to find some control parameter. And as we practical physicists are not tied to the bounds of reality, we can promote the fields to transform in some non-trivial representation of SUN. In particular, we'll consider a model of fundamental fermions and adjoin the scalars. And we will take n to infinity. So we have a well-defined problem, and we can solve the theory by resumming all the planar diagrams and solving the Schwinger-Dyson equations. And this is what we do. And the main result is what one obtains for the fermionic self-energy. It has two important ingredients. The first feature is that it scales with some power of the frequency, which is less than 1. So some point for frequencies low enough, one would expect this quantum correction to dominate over level linear dispersion. Where it happens is given by this scale, this dynamically generated scale, which we call lambda, and it is the non-Fermi liquid scale. And essentially what we get is that for energies below lambda, the effective dispersion relation of the degrees of freedom is given by this omega to the 2/3 and of course the momentum dependent piece. So we say that the fermion here has a dynamical critical exponent of half. Let me emphasize that this is precisely the benchmark of non-Fermi liquid dynamics, because now the green function, for the green function, we replace the usual pole-like structure by a more complicated one involving some branch cuts. So for sure, in this model, there are no quasi-particles. This is the non-Fermi liquid. Moreover, one can check that the coupling an order 1 value. And so, oh, I think I touched something. Okay. And so the model below this dynamically generated scale flows to an interacting non-Fermi liquid. A last remark about the quantum critical point.
I have a question.
Oh, yeah.
So is this value for the value of z, 3/2, universal in some sense, or okay, it is the result.
Well,
this model and different models will have different
yeah, of course.
values.
Yeah. It has some degree of universality if you want, in the sense that in principle there could have several order Z=3 bosons, and half comes essentially because there is a Z=3 boson running on the loop. If Persian relation for the boson different, you have a different fractional dynamical exponent. So yeah, that's the degree of universality. If there are several systems and Z=3 scaling for fluctuations, then yeah, you will have a Z=3 for the fermions. Yeah, but so far I'm not sure about the particular implications of model, actual samples. It's a theoretical model, but in its own, yeah, you could say that it's universal. Okay. So a final remark about the temperature dynamics is the following. Of course, the model is a scale invariant. In particular, here I display the scale invariant, the scale transformations of the bosonic degrees of freedom, because you can use them to check that the possible quartic self-interactions are ruled out because they are under this scaling. And this is consistent with the fact that we haven't taken into account. But this point will be important at finite temperatures. So let me try. Okay, I think I'm more or less okay. So let's find temperature picture. So before going to the particular details of the computation, let's just briefly describe the naive expectation for the quantum critical region. So far we have seen that there's dynamically generated scale lambda, and as soon as we turn on the temperature, we introduce another scale, which is the temperature. So in principle, this will be the only two scales in the problem. So it makes sense to assume that the quantum critical region essentially ends when the temperature becomes of the lambda, because if we have only two, the temperature can be lower or bigger, and there's no much space for new things to happen. Of course, the lateral crossovers of the quantum critical region will be given by the 3/2 scaling. And by definition, inside this region, the scaling of for instance, of the fermionic self-energy has to be dictated by the critical point at 0 temperature. So this is what one expects to happen, but of course it doesn't. So at first point, one could say that it is a bit counterintuitive, but because there's no obvious new scale, which is here. But one can realize that there's something that we missed in our naive expectation, and is that in 2+1 dimensions, the model becomes ill-defined when we consider finite temperature, and we will find exactly how to solve it. And in the way of solving the divergence, we will find that the new scale is generated and will imply a richer structure for the critical region. So let me give you, before going to the technical part, let me give you essentially a taste of the physics involved in finite temperature and why where these IR divergences originated and why they are so severe in 2+1 dimensions. So, well, the reason is the following. So in Euclidean spacetime, you all know that turning on finite temperature is essentially doing a circle compactification, where the bosonic degrees of freedom will satisfy periodic bound functions. So the spectrum of frequencies will be quantized in terms of some integer multiples of pi and the temperature, of course. And here we have two very different scenarios. On one hand, on the right-hand side, we could have non-zero frequencies. They still have Landau damping because the Landau damping term is proportional to the frequency. As we will see, they make regular contribution loops. And as we also will see, they induce essentially the finite temperature extension of the quantum critical self-energy. So they do not add nothing new at finite temperature. On the other hand, there's a new ingredient, which is the static mode with zero frequency. So it doesn't care about Landau damping because it has zero frequency, but moreover, it doesn't know anything about the thermal circle because it doesn't depend on this direction. So it's really a two-dimensional degree of freedom. And we know that scalars in 2 dimensions have a green function which grows logarithmically at large distances. And essentially, these are the IR divergences that we will find. And since they are not Z=3 bosons, a bit late will induce a different scaling, which won't be 3/2. And we will see that. And so finally, these static modes are essentially the manifestation of thermal fluctuations, and they dominate at high energies where this circle is very small. And so the non-zero frequency modes are effectively gapped out, whereas the other contribution will dominate at low temperatures, and from this condition we find a dynamically generated scale. So this is essentially the story. Now let's see how it happens in this model. So in order to see this, we will split the one loop contribution to the fermionic self-energy into the contribution of static modes and the contribution of the rest. So the contribution of the static mode is what we call the self-energy, is the new ingredient here. And as we can check, it diverge logarithmically when the momentum goes to 0. This is the IR divergence. The other contribution, we will see that it's completely regular, and we can explicitly compute it, and it doesn't add too much information. But so the main point here is that the competition between these two contributions is essentially what will lead to a richer diagram in the critical region. But before evaluating any competition between these two contributions, we have to regulate the infinite one. So usually here, this process of regularizing air divergence is usually try and error. It is, in general, very instructive to check the failed attempts, because one usually learns something from them. But for sake of time, because I'm doing, I'm going more or less 40 minutes, because I turn on this late, so I have more or less 25 minutes. Okay. Well, so maybe we can check the failed attempts. It's very short. So the first obvious thing that one could expect to resolve these singularities is that somehow a mass term would generate for these static modes. And the first source of a mass term are, of course, fermionic loops. But one can check that at finite temperature, fermions still lead to something pretty much like Landau damping, but subleading. So this is not the actual answer. A bit more elaborate attempt, which has been very successful in the past, is to appeal to non-perturbative resolution by resumming all diagrams, in this case the planar diagrams, and hoping that the ending result be regular. Let me just emphasize that this mechanism works perfectly in 3+1 dimensions, and due to the fact that IR divergences are very strong in +1 dimensions, we will see here that this won't work. So essentially, the recipe is that you define the same integrals in dimensional regularization. You write down the infinite sum of planar diagrams, and you solve the equation self-consistently. And it turns out that this resummation process somehow tames the because it turns the 1/epsilon divergence 1/square root of epsilon divergence, but still is not enough. So it turns out that the actual resolution of these divergences is a bit more subtle, and it can be achieved by bringing in some interactions that we have discarded so far, because they were irrelevant at temperature. And these interactions are the quartic interactions, of course. So let's see why we have to include them here. And the is that if you quartic self-interactions for the bosons were ruled out by the Z=3 scale, but we have said bosons doesn't satisfy Z=3 scaling. So it will be reasonable if these interactions become relevant for this, and this is what happens. So in order to see that, one limits to the energy and momentum scaling, which the static mode dominates, and under some non-important redefinitions, this is the effective theory. It's an effective two-dimensional theory for the static boson with quartic interaction. And under the same rescaling that leaves the fixed point invariant, we can check that now this coupling is relevant. So it has to take it into account. So this is sort of a close casting of something named dangerously relevant couplings. I'm mentioning this because maybe someone knows what it is. It's not very important for us. The main point is that being this relevant, we cannot ignore it anymore, and we will see that out of this self-interaction, a new mass term will be generated that will resolve the IR divergences of the model. So long story short, what one do is just resum all the planar diagrams corresponding to this quartic interaction for the static boson, and solve the equation self-consistently to obtain this mass, which of course is proportional to the temperature because it is an exclusively thermal effect. And now the static boson propagator will have a mass term, and so the problem is solved, at least the problem regarding IR divergences. So now we can proceed to actually solve the model at finite temperature. Before doing that, let me recall you the competing effects that are here. So on one hand, we had the thermal component of the self-energy. This accounts for the contribution of the static modes, which are essentially the thermal fluctuations. This is resolved by the thermal mass we just saw. And we will see that this also vanishes zero temperature as it has, because the quantum critical point doesn't know about this thing. And in the flywheel, we'll see how a new scale appears. On the other hand, the other competing effect is the quantum, let's say, from liquid component. And as I mentioned many times before, this doesn't introduce nothing new. It just is the naive extension to finite temperatures of the quantum critical scaling. So let's start with this, which is the more easy one. So one can see this by explicit computation. It has this form, and essentially it goes continuously to zero temperature. It reduces to the quantum critical self-energy at zero temperature, and it now, with respect to the temperature, it respects the 2/3 scaling. So nothing new here. Oh, okay. The thermal self-energy is a bit more complicated. You have to solve it numerically, but there's a regime which is the one we'll be interested in, of low energies, low enough energies, in which it can be approximated by a constant in the sense that it doesn't depend on the frequency. So in this regime, we will see that this is the only regime in which it can dominate over the quantum part. For higher frequencies, it always loses. And the end of this window in which this can be approximated by a constant is given by this scale lambda p, which is the promised new dependent scale. So if we find that at some point this sigma t with this constant approximation dominates, we will have an explicit violation of the critical point scaling, because it now goes with T+1. So this is a summary of what I just said. Let me check if there's something new. Well, the only new is of terminology. So in the regions, we will now proceed to characterize the quantum critical regions and the limits, all the portions of this phase diagram in which the thermal fluctuations dominate. And whenever it happens, we will say that we are in presence of a thermal Fermi liquid, because still doesn't have Fermi liquid scaling, but is now completely induced by thermal fluctuations. So no memory of the critical points, but it's still a non-Fermi liquid. So in order to do that, let me just establish some hierarchy in the parameters. This is not necessary, but it's just in order to have 3 well-defined regions. So the first region is the obvious one, is zero temperature, where the quantum critical points exist. And so it has only quantum critical scaling. The second region exists up to a window, within a window of temperatures given by this, well, for the temperature bigger than 0 and less than this scale lambda over g squared lambda is written this way in order for you to realize that this is lower than lambda. And in this window of temperatures, we will find the 2 non-Fermi liquid scaling. The first frequencies up to lambda t, we will find a thermal non-Fermi liquid. For within a window between lambda t and lambda, we will find quantum critical non-Fermi liquid. Let me just emphasize that if the temperature is low enough, this lambda t is very small, and the window of quantum criticality is very large in comparison to the thermal non-Fermi liquid. So this second region is what one associates quantum critical region associated to the quantum critical point. But as the temperature increases, this window starts to shrink and eventually disappears, and we end up with the third regime in which there's only thermal non-Fermi scaling. Of course, for frequencies large enough, we will always have a linear scaling, but not. So this is our true quantum critical region, and let me time describing it. So first of all, we realize that the proper quantum critical region, which is the orange one, is smaller than expected because it goes up to a scale which is not lambda, but lambda over g squared, which is lower than lambda. This physically can be seen as a remnant IR divergences, because even though they are regulated now, they are so severe that even after regularization, they destroy the quantum critical scaling at energies below lambda, which is the quantum critical typical energy. So below this lambda over g squared scale, there's a new Fermi liquid, which we call thermal Fermi liquid. And of course, the lateral crossovers will go with the corresponding dynamical exponents in each. So, oh yeah.
Sorry. In the previous, in what you call the thermal non-Fermi liquid phase, is it?
We have this one?
Yeah, so
okay.
At point 2, I'm a bit confused in the sense that I find counterintuitive that for very small energies, you are in the thermal phase, and then you go to the quantum phase for higher energy.
Well,
is it counterintuitive or not?
Yeah, what happens here is when you go from 1 to 3, there are more frequencies which fit into the thermal non-Fermi liquid. Because at this point, you may say, okay, but in the second region, there's still low frequencies which still fit into the thermal non-Fermi liquid. But what we say is at low enough temperatures, still the second region is the bigger one. Of course, this crossover, it's just an estimation. But usually this, so let's say that a more precise definition would be that the quantum critical region is extend over temperature such that the intermediate region is still macroscopic in comparison with the first one. Yeah, is that the question? Or?
Well, my question was, I would expect the opposite, right? For higher energies to be in the thermal behavior or not? No, I don't know. That's.
You would expect the opposite.
I mean, in that region, I would expect that for smaller energies, you have like a quantum non-Fermi liquid. And
Oh,
for
yeah,
higher,
yeah, 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 yeah. I see what you mean.
I don't know, maybe
Uh,
it's just my intuition, which is wrong.
I think it's the intuition. It's reasonable. So the fact that the thermal piece dominates for lower frequencies is just because it's scaled with the lower power of the temperature. So that's the. I don't know if I would expect the opposite to happen. In principle, what determines the relevance of the fluctuations is which one dominates over a wider range of frequencies. It doesn't matter if you have like 5 frequencies in thermal, but 100 in quantum critical, you can, that this is a quantum critical. Yeah, it might be intuitive. So, okay, let me use the, how much time do I have? 5 minutes? Okay, perfect. So let me go very quickly about the superconductivity. So as you can imagine, superconductivity of a non-Fermi liquid will have many new interesting features, both due to the quantum and thermal effects. I think one of the most remarkable ones, it's purely due to quantum effects, so we can see how it arises already at 0 temperature. And the physical reason for this to happen, as we will see, is due to the sort of dual effects of the gapless boson. So on one hand, what we have been extensively along the we have seen extensively along this talk is that gapless boson running on loops usually tend to destroy the quasi particles and induce an anomalous dimension, the fermionic degrees of freedom, which is what we associate with non-Fermi liquid. Something that one can check is that new scaling behavior of the fermion actually renders the BCF coupling irrelevant. Or if you want, in a more physical language, in order to form a pair, you need to have two well-defined particles. And if you destroy the quasi-particles, the tendency to form Cooper pairs will be suppressed. So the first effect of these gapless boson fluctuations is that they usually tend to suppress superconductivity. But on the other hand, you can check, computing this simple boson exchange diagram, the very same boson that generates the non-Fermi liquid scaling also generates singular contribution to the BCS vertex. And I say singular, I mean that it goes with first powers of the energy. So it tends to grow a lot at low energies. This important contribution is not new, was already considered in color superconductivity, and it's crucial for what we will see, because now we have, again, a compete of two effects. And let me just emphasize that the non-Fermi liquid effect is a planar effect, with something stronger as n goes large, whereas the BCS vertex is usually non-planar. So this singular contribution becomes important at lower values of n. The non-Fermi liquid scaling becomes important at larger values of n. With respect, point in the middle, something special to happen. And this is essentially what happens. So we have a particular critical n when there is an infinite order phase transition. So maybe I will end up with this. So this infinite order phase transition can be already seen by perturbative approach. So here is the beta function of the BCS coupling. So the last term, in the rightmost term, is the usual one loop contribution that makes the BCS coupling relevant, which is already present in Fermi liquid, so nothing new there. So the first two terms are the important ones, which come with different signs signaling this competition. And so we have the boson exchange is the first term. The second term is the anomalous dimension, so it's the non-Fermi part. And so we have that if there are some fixed points of these beta functions, they are given by solutions of the important thing about that is that we have a square root, which may become imaginary. So we see that there are two fixed points. The lambda minus, it's IR stable. The lambda plus is UV stable, but we have two, which are real, so they exist when the n is large enough, is bigger than 8 in this case. And that means that for n bigger than this critical value, the non-Fermi liquid part prevails, and the system, instead of going to superconducting phase, goes to a non-Fermi liquid, but now with finite BCS couplings. As we decrease the value of n, these fixed points will approach each other, and at the critical value of n, they will collide, and eventually they will go to the complex plane. When after this happens, the BCS coupling will have no other option to infinity, and the model will go to superconducting phase. This collision of fixed points usually leads to something called BKT transition, which are infinite order phase transitions, very interesting ones. And this is essentially what happens here. And you can see it by computing the correlation, which, as you can see, diverges, but in a non-analytic way. So I think I won't have to continue, so maybe I can end up.
Okay, so we have time for some questions.
Can I ask, like in the just previous slide?
Mm-hmm. Oh.
So it seems like, so this d lambda over d mu is like a beta function, right?
Yeah, it's the beta.
So there is even a term to the beta function coming from a tree level. How does it work?
You can say that this boson exchange is sort of a tree level because you can obtain the integrating out the boson.
Yeah, but so it's a bit unusual, right? Usually the beta function just comes from some logs in loops. So
well, but that occurs if there are fractions. That's essentially what happens here, the third term. In a Fermi liquid, you don't have this. You only have this. And this comes precisely because this one loop diagram is logarithmically divergent. And this is the first contribution because the coupling is marginal at tree levels. But now, the singular contribution of the boson makes the coupling, well, not completely relevant or not completely irrelevant. There's a competition between these two guys. But the coupling is not marginal anymore. That's the main point. So it's a very good question. Yeah.
okay, thanks. No, sorry, I also have another curiosity. Like, was it crucial that the scalar, the boson, was a matrix in this large n limit? Like, could you also consider simpler example? Like, you consider some large n limit in which the boson carried two indices, right?
That's also, yeah, that's for the definition of the critical, because actually I think you can define physical that made is a singlet, but fermionic degree, which is called Berg-Larsen model, you can find that you quantum critical in this limit.
Okay, thanks.
The reason.
Do we have more questions? Maybe from people online? Okay, so if not, let's thank Jeremias again.
Thank you.